Hello, this is AP Chemistry Chapter 10 on Vesper, and we're going to finish up going over bond polarity and hybridization. So in order to determine the polarity of a molecule, we have to do a few things. We have to draw the Lewis structure of the molecule and determine its molecular geometry. That means whether it's linear or trigonal planar or tetrahedral. We have to determine whether the molecule contains polar bonds, so we need to know the difference in their electronegativities. We need to know if the molecule, contains two identical atoms, like chlorine to chlorine, for example, or hydrogen to hydrogen, or if it only contains carbon and hydrogen. Those are called hydrocarbons, and they are typically oils and fats, like a fossil fuel would be an example. Or if they're symmetrical, so if they're perfectly symmetrical, then all of those are going to be nonpolar. If the central atom in a molecule has one or more lone pairs, that's automatically polar. And if it's not symmetrical, it's going to be polar. Okay, so let's look at some examples. These are the Lewis structures that we drew earlier. And we are going to talk about the polarity this time. So the difference in electronegativity between beryllium and chlorine is going to be significant, meaning the chlorines are going to pull the electrons towards them in each direction. Okay, but if you were to take a mirror and split this molecule, let's use blue for our mirror. So if you split this molecule vertically, it's going to be symmetrical. It's the same on both sides. If we split it horizontally, the top looks exactly the same as the bottom. You would have half of a chlorine atom on each side up top, and the other half would be on the bottom. Okay, remember that these are mostly spherical shaped atoms here, so don't think of the Be being upside down, think of the beryllium atom being upside down. So because this is symmetrical, I have two poling atoms in opposite direction with the exact same strength, so the pole of the chlorines are actually going to cancel out, and there will be no net dipole moment, meaning nobody can hog the electrons. So polarity for this guy is going to be, I'm going to put in for nonpolar. Okay, so that guy is nonpolar. The next one is not the best example, because this is technically an ion. This is negatively charged. So polarity, this would be ionic. Okay, now if we can use our imaginations and pretend that it was not ionic, so it's some other trigonal planar molecule, even if it has the resonance structures, if all of the atoms bonded to the central atom are the same, and they are, and if it has no lone pairs on the central atom, which it doesn't, then this would be nonpolar. So another molecule that would have three identical atoms bonded to it, a good example would be BF3. Boron trifluoride is going to have three fluorines bonded, all single bonds, and since they're all exactly the same, it would be nonpolar. Okay. For this one, this bent, I see a lone pair of electrons, meaning this side of the atom is going to be more negative than the bottom half. So this one is going to be polar. Okay, also it's not symmetrical. The top looks different than the bottom. That lone pair of electrons is different than the oxygens down below. For the tetrahedral here, I have four fluorines. They are pulling, because they're the strongest electronegativity of all atoms, and they're pulling in opposite directions. So picture four crazy wild horses with a ring in the center. If they're all pulling exactly the same strength in opposite directions, then that ring will stay fixed in the center. It can't be pulled in any direction because they're all the same strength. So this is nonpolar. It's also symmetrical. It's harder to tell with this one, but it is symmetrical on all sides. For this one, this lone pair automatically makes this polar. We have two lone pairs down here, and water is one of the most polar molecules. This one has lone pairs too, so this would be polar. Okay, so Hopefully you got polarity. Let's go back and talk about hybridization. So for hybridization, the orbitals in a molecule are not necessarily the same as the orbitals in an atom. We talked about s, p, d, and f orbitals in an atom. When you put them together, make a molecule, those s, p, d, and f orbitals change, and we get hybridization. Hybridization is a mathematical procedure in which the standard atomic orbitals are combined. So we're going to combine s and p orbitals to form a new atomic orbital called hybrid orbitals. We can use the molecular shape. So the math is beyond AP chemistry level. That would be something for college. We can use the molecular shape to determine the type of hybridization pretty easily. So if it's tetrahedral, that means it has a steric number of 4. It's going to have sp cubed hybridization. The exponents, you can think of the s as being to the first power, okay, or having one of those s orbitals, and the 3 p orbitals, they're always going to add up. So the top numbers are going to add up to how many things are around the central atom. So tetrahedral 4, the top numbers need to add up to 4. 1s and 3p makes 4 total. Trigonal planar, the 3, you have 1s and 2p orbitals. We need to add up to 3. So trigonal planar is going to be sp squared. And then linear, we just have 2, a steric number of 2. So we only need 2 orbitals, 1s and 1p. So it's sp hybrid. Okay, so down below, we can see methane, CH4, there's its Lewis structure. It's going to be a tetrahedral shape, and it's going to have 4 sets of electrons around the central atom, meaning I need 4 of these hybrid orbitals, so sp cubed. So the 1s and the 3p add up to 4, and there are 4 sets of electrons around carbon. So this is sp cubed. Let's do some more examples. Okay. So hybridization of beryllium chloride, we're just looking at the hybridization of beryllium, the central atom. And since there are 2 things around it, I'm going to need S. Let's use a different color. We'll use purple for hybridization. SP, 1S and 1P will give me the steric number of 2. So that's SP hybridization. When you have 3 things around the central atom, like NO3 or BF3, you're going to need SP squared. You need 2 p orbitals to combine with the 1s orbital. And for SO2, I still have 3 things around the central atom. So the hybridization on SO2 is going to be sp squared as well. For carbon tetrafluoride, we have 4, a steric number of 4, meaning I'm going to need 4 orbitals to hybridize. So 1s and 3p need to come together to give me an sp cubed hybrid orbital, or hybrid orbitals, I should say. And then the trigonal pyramidal, we still need a place for these electrons. The steric number of 4 means I'm still going to have sp cubed. And same down here with water. This is an sp cubed hybridization for a steric number of 4. Okay, last but not least, let's talk bond angles. So for linear, the farthest apart these chlorines can get from each other is 180 degrees. So that is the bond angle. They're going to tend to be 180 degrees apart. For trigonal planar, we have their flat, they're planar, so it's 360 all the way around, divided into 3 parts, which gives me 120. So this is 120 degrees. For the bent shape, I'm going to put that it's just a little bit less than 120 degrees, because these lone pairs of electrons around the sulfur are extra repulsive. They're going to push the oxygens a little closer together, so the angle between the oxygens is going to be just slightly less than 120. That's our bond angle, the angle between the 2 bonds. Okay, for tetrahedral, remember it's 109.5 degrees. when I remove one of the bonded atoms and replace it with a lone pair of electrons, it pushes the hydrogens a little bit closer, so this bond angle is going to be just slightly less than 109.5 degrees. And then this one would be the smallest. We can put less than, or just less than. You don't have to be extra. Okay, it's less than 100. So that's basically, this would be like small, medium, large. This one is the biggest bond angle of those three, the medium, and this is the smallest bond angle of those three, if we were putting them in order. All right, I hope you guys understand bond angles and polarity, and hybridization. If you have any questions at all, feel free to send me an email and we'll discuss it in class. Have a great day.